We will go now to University of Washington. The first presentation, exploring the combined use of distributed fiber and deformed bar reinforcement to resist shear forces. Dr. Travis THONSTAD is going to present that. Dr. THONSTAD.
Thank you so much. Okay, so today I'm going to talk to you about the combined use of distributed fiber and deformed bar reinforcement to resist shear forces. This is a project at the University of Washington with myself and with Paolo Calvi. We have 3 students that have been working on this project. John Paul Gaston, who's been doing a lot of the testing. Benedict Farag is a new student from part of our Valet program, and he's been doing some of the numerical modeling. And we also had a student over the summer who was doing some testing as well. So that's Alexander. Let me see, hopefully I can advance. There we go. So why are we looking at fiber reinforced concrete and accelerated bridge construction? So FRC enjoys widespread use and practice already. So it's required in several states for bridge decks, and the improved serviceability and durability of PVEs made from FRC would create an additional incentive for owners to choose ABC techniques over other alternatives. So certainly UHPC is one type of fiber reinforced concrete, but there's also lots of other fiber reinforced concretes that are used in practice to improve durability. And so what are the benefits of macrosynthetic? So obviously, steel fibers are one option. The other option, it would be macrosynthetic fibers. And the advantage of using these macrosynthetic fibers is going to be, of course, the improved durability and ductility of the concrete. Those fibers are going to bridge between cracks and keep those crack widths smaller. And that's what we know and why we use these fibers in practice. And what we're really exploring here in this project is, could we alleviate congestion and reduce the required amount of deformed bar reinforcement? So could we use these fibers that are placed there for durability? Obviously, they contribute to the strength somewhat, and so could we use the strength of these fibers for structural applications? And the challenges with that is that the strength contribution of these macrosynthetic fibers are not recognized by the code, and there's really limited amounts of test data out there to allow us to make some recommendations. And so the project objective is to develop rational design equations for the combination or the combined use of macrosynthetic fibers as supplementary distributed reinforcement. So this would be in addition to your conventional deformed bar reinforcement for shear. And looking at what's out there in terms of research, the previous research has really focused on steel fiber reinforced beams without stirrups. And so if you look at the bar chart there on your right, that's the last 40 years of research on fiber reinforced concrete. And you can really see that for the most part, everything is the gray bars. The gray bars are SO, steel fiber reinforced concrete without stirrups. There's really limited testing of structural elements that incorporate both fiber and deformed bar reinforcement. Those are the blue bars, but even then, those are typically steel fiber reinforced concrete. And almost all of the data that we have is looking at beams, and so you have some combination of flexure and shear that's inherent to that test method. I'm going to highlight one of the tests that's in that database, and that's a test that was done on both fiber reinforced, so synthetic fiber reinforced concrete and also steel fiber reinforced concrete. It was an interesting test study in that they tested beams both without stirrups and fibers, some beams with fibers but no stirrups, some beams with stirrups but no fibers, and some beams with both stirrups and fibers. So they kind of hit all the corners of the square. And what was interesting about that is then they could start to look at what was the contribution from each of these different components. And you can see, of course, we have some contribution from the concrete. If you add stirrups, that contributes some as well. The fibers contribute a little bit as well. And there was this added benefit. So that's what they are calling synergy in this picture. And that added benefit was when you had both of the fibers and steel together. And so that's really what we're exploring in this project is what is going on. Can we quantify that synergy there in a meaningful way? So again, when we think about shear resistance of structural elements, we know that there's contributions from a number of different sources. And really the question we have here is, should we add an addition from those fibers? And of course, beam testing is one way to go about it. Kind of a more direct way to look at shear resistance would be to extract some shear panel from your element. And in order to do that, you need to, so if you're going to test shear panels, you need to have a specialized shear tester. And thankfully at the University of Washington, we have one of those. And so that makes us uniquely situated to look at this. So here you see the panel tester in our lab. You have a rigid steel frame, which is going to be used to react all of the loads. You have your panel test specimen there, which is the diamond-shaped specimen there in the middle. It's being, so we're applying an in-plane stress state using 37 hydraulic actuators, and those are all being controlled by a hydraulic load maintainer, a hydraulic power unit. So we're applying a state of known stress, and we can apply any state of in-plane stresses in terms of pure shear or shear plus axial, shear plus tension. And then we're measuring the strains using a non-contact instrumentation system, which is really just keeping track of the location of these LED targets that are applied to that front surface. So the research program that we had in place here, so we have the first part of it was to develop a database of tests of macrosynthetic fiber reinforced concrete. You saw that bar chart there at the front of the presentation. So that phase of the project is complete. Then we were going to perform experimental tests to investigate the combined use of deformed bar reinforcement and macrosynthetic fibers in concrete, to resist those shear forces. And I am happy to report that as of this presentation, we're now finished with that. So I get to finally present some results of that test campaign. So the test series, we ended up testing 12 panels in all. They had 3 volume fractions of fibers, so both panels without any fibers, then panels with 0.26% and 0.52%. And those percentages seem a little odd, but it's really 4 pounds per cubic yard and 8 pounds per cubic yard. And 8 pounds per cubic yard is actually the maximum addition rate that the fiber manufacturer recommends. And in the longitudinal direction, all the panels had 2.3% steel, and in the transverse direction, we then had 4 different levels again. So we had, of course, no transverse reinforcement up to the maximum transverse reinforcement that would be allowed for this specimen size. So here's what that looks like in terms of the reinforcement layout. So you can see in all cases the steel that's going from left to right horizontally is the same in all sets of the panels, and really all we're varying then is the reinforcement in the vertical direction. So the specimens with 0.29% had 3 bars, with 0.58 had 5 bars, and with 1.14 had 10 bars crossing the test region. And the test region is really that portion that's in the middle of the panel there. Once you get past those headed bars that are there to help anchor in these rigid blocks. And those rigid blocks are there to allow us to attach it to the test machine and apply those shear forces. The type of fibers that we were using in this test series, they are GCP Strux 9040. They have a long track record of use in both experimental testing and also in practice, and so they were because they had that track record, they were useful for our purposes. They're 40 millimeters in length, have an effective aspect ratio of 90. You can see the dimensions there on the bottom. They're essentially a tape-like fiber with a high elastic modulus and tensile strength. So that's why they were quite useful for this test. To build these panels, you start with a casting table and these steel anchor blocks. You then take all of your reinforcement. All the rebar is actually threaded on its ends, and it's passed through, and then it's attached to the blocks with nuts. And so that was something that JP had spent a long time doing. He had to thread a lot of rebar. You can see there the fiber addition. So we have a concrete mixture, which we worked with Cal Portland to get that, and now we're adding the fibers and then placing that in the casting table here on the bottom row. So we had an external vibrator that helps to consolidate the panel. We found out later in the test series that we also needed to use a little bit of internal vibration along the edges of the panel to make sure we had really good consolidation around the edges. You can see specimens were wet cured for 7 days with wet burlap and plastic, and then were tested after 28 days. So here's the test procedure. Again, we have our diamond-shaped panel where you can see that we have our longitudinal reinforcement going diagonally in one direction. We have our transverse reinforcement going diagonally in the other direction. And we're applying increasingly, so monotonic, but increasing shear force in increments through those hydraulic actuators. And it's really those actuators acting in tandem. So the vertical actuators are pushing down, the horizontal actuators are pulling out. And so in the combination, they're of course providing that pure shear. And so as you'd expect, the cracks predominantly form vertically in the panel. And so those are in the direction of the principal tension. And then you eventually get failure along the longitudinal reinforcement. So that's what you see in the big crack there. That's the final failure surface, which happens along that longitudinal reinforcement. And so I just wanted to show you a picture of some of these failures. So the panel on the left has no fibers. The panel on the right has the 0.52% fibers. And as you'd expect, one of the things that you can notice is that there is just a better distribution of cracking in the panels with fibers than without. So we are having fibers that are bridging those cracks and are allowing you to form those additional cracks. So now I finally get to show you all of the data. So this is the normalized shear stress in terms of F prime C. Sorry, the plot there had some weird characters happen. And the x-axis is the shear strain. And so you can see very clearly the 4 series in terms of the reinforcement ratio. And as expected, the shear strength increases with the transverse reinforcement ratio. That is sort of the obvious conclusion. You can see that the panels with no transverse reinforcement are sort of occluded by all of the other lines here, but their responses were quite similar. What you can see from this plot, there's a couple of things to notice. It looks like there might be some influence of the fiber volume in terms of the strength. So this is kind of hot off the presses, so we're still working through the statistics on all of this, but you can see that at least for these high reinforcement ratio tests, that there is potentially some increase in shear strength using those that higher volume fraction of fibers. When you get down to the lowest reinforcement ratio, you do see an improvement in the sort of strength and deformability. And in the middle here, you can see that there's some trends that maybe don't quite make sense in terms of the fact that the panel without any fibers looks like it did quite a bit better. And unfortunately, this was the first set of fiber reinforced panels that we tested, and we had some consolidation issues around the edge. And so we're attributing some of that strange behavior to those consolidation issues. And I'll show you what that looks like and why we think that might be the case. So here you see what the edges of those panels look like. Of course, you can't actually tell how bad things are until you take the blocks off at the end of testing. But you can see the honeycombing that's on the outside of that panel. Excuse me. You can see the corner damage that happened during testing, and you can really see the honeycombing on the bottom surface here of the panel during testing. So there certainly were some issues with this panel, and we think that's why we're seeing what we're seeing in that plot. So we're seeing if we can retest these panels. It would be great to really see if that's what the cause was, because certainly it's showing a different trend than the other sets of tests. So some of the things that you'd hope for in terms of the addition of fibers, you'd expect that the crack widths would decrease as you add fibers. And so first I was going to show you average crack widths. So here's the average crack width as a function of both fiber volume fraction, the plot on the left, and as a function of transverse reinforcement ratio with the plot on the right. And as you can see, in both cases, the average crack width decreases as the volume of fibers or the transverse reinforcement ratio increases. And so you can see there's a few data points there that look a little weird. Those are those panels that had consolidation issues. But in overall, the general trend is true. So you see that makes sense. That's what we expect. Same thing's true of the maximum crack width. So this is again at a stress level about 6 roots F prime C. And you can see we're comparing 3 different volume fractions from 0% to 0.52. And the maximum crack width, again, decreases as the volume of fibers increases. So that's exactly what we hoped for, and that's what we saw as well. So that's good news there. So again, we're still processing the data, and we're still digesting what we're seeing out of it. But I think some of the preliminary observations here is that macrosynthetic fibers are effective at decreasing both the maximum and average crack widths during shear loading. That's sort of what we would expect and what we're hoping to see. There appears to be some benefit of adding macrosynthetic fibers in terms of strength and deformability at the addition rates used in the study. And again, these were pretty low addition rates. 0.52% is not very high in comparison to some of the other tests that have been done up at 1 and 2%. And we're still digging into that, and we're hoping to be able to do some statistical analysis to show whether or not that's significant. The benefit of adding fibers may depend on the transverse reinforcement ratio, and this is really looking at that plot a little bit more carefully and seeing that you might actually get more benefit at the lower reinforcement ratios than you do at the higher reinforcement ratios. And that might make sense in terms of thinking about the behavior and the mechanics there. So the next phase was to develop some new design equations for the shear strength of macrosynthetic fibers based on a rational shear behavior model. And that rational shear behavior model is based off of the modified compression field theory. And so obviously it was developed using panel element testers, and it forms the basis for the shear codes in the AASHTO code. So it makes sense that this would be the way to go. So you can see kind of starting from the mechanics on the left, looking at principal strains in the panel on the middle, and then converting those strains to stresses using constitutive relationships, which we can then calibrate to what we've used, what we have in the test. So we have a student right now that's looking at this in both Membrane 2000 and Vector 2. They're finite element programs that are both based off of the modified compression field theory. And his job there is to calibrate the constitutive relationships and modeling approaches based on these tested panels. And he's making great strides so far, so you can see that here. So this is one of our panels without fiber reinforcement. And so you can see, as you'd expect, the vector model is doing a great job at capturing that behavior. Of course, once you add fibers, then you need to modify things, and that's what he's working on now. And the hope is that we can use the companion tests that we've done. So this is ASTM 1609 beam. Excuse me, sorry, I'm a little under the weather today. So we're hoping that he can use these tests of these beams that show the flexural relationship here, so you can see the residual strength and the change in residual strength caused by the fibers. So what's next? So we're going to be calibrating the FEA models to the experimental tests. You can see some examples of some preliminary data there on the right. We'll be performing a parametric study to extend the results of the testing program. Of course, there's a lot of panels that we would have loved to test, but didn't have the resources to do so. And so this will give us an opportunity to really expand out the scope of our testing program. And then we'll be using existing empirical relationships and potentially some new recommendations for then structural members that contain both fiber and deformed bar reinforcement. And the idea would be to have, again, some equations that would then include the contribution from macrosynthetic fibers on the shear strength of your concrete elements. And with that, I'd like to say thank you very much for listening, and I'm happy to take any questions. I might have gone a little into my time there.
No, you did very good. So Dr. Townsend, thank you very much. We don't have so much time for that question, but I want to make a comment on your shear testing apparatus. We had it in one of our seminars. It's really a great advantage to have that kind of setup.
Absolutely, yeah. We're very happy that Dr. Calvi came to UW and was able to bring that capability with him.
Thank you very much.